Welcome everybody. For most people, I guess it's morning, whether you're in Scotland or southern tip of South Africa. A few of us over in Australasia. Welcome back those who were with us last week and last year, and we've got a few new names too. So hope you enjoy today and the next ones that are following up. This is part of a collaboration between the Overberg Geoscientists Group and Melbourne University Gold Course and Stellenbosch University. People like Henny, John, and others make this possible, and we get a bunch of speakers from around the world who give their time voluntarily to educate us all and give us cause to debate and discuss different aspects of gold. The focus for the next week or two, aspects of the Witwatersrand gold particularly, although it's got application elsewhere. And the reason there is we were left with quite a few quite interesting and outstanding in some ways questions at the end of this session 12 months ago. We thought, well, let's put those on the table and see if we can get some experts in and talk about them. Things like carbon, things like sedimentology, and in this case, it's the quartzites. And today it's Jonathan Law talking about the Witwatersrand Quartzites, a major rock type, of course, and yet so often overlooked or not looked at in detail. Jonathan worked in the mid-80s with Gencor on Kinross Mine on the far east out in the Evander goldfield, and then went to the other end of the whole goldfield, 300 kilometres away, and looked at St Helena for another project with Gencor before he joined them. Worked for several years in a pretty exciting and enthusiastic, motivated group of geologists looking for new ideas, and later on moved to Australia. Spent some time in industry in Western Australia and Central Australia, and has been with CSIRO, the government research agency, until about 18 months ago when he retired there. So I'll hand over now to Jonathan Law.
Great. Thank you, Neil. And thank you, everybody who's joined us this morning. It's certainly a great pleasure to be here. And looking through the list of speakers that are coming up and having watched some of the videos over the last couple of months, it's been a fantastic forum that's really generated a lot of interest and discussion. So very happy to be part of it. I wanted to just start by thanking some people that have been with me on my Witwatersrand quartzite journey, which, as Neil just said, started back in the 80s and through the 90s. And really, without these people, I probably wouldn't be here talking about this today, because they really were pushing against the current, I guess, back at that time, and supported me and colleagues really strongly through that period. So Neil, Tony Cadle, who are my thesis supervisors, Eric Tweedy at Gencor, along with Gordon Cole, who really supported the work that we did and paid for it and kept it going in difficult times. Andrew Bailey and Richard Spencer, who worked with me on various research aspects, and Mark Coward and Annie Barnicoat, who were consultants to Gencor that really moved some of the thinking along as well. And the quartzites certainly do have some interesting stories to tell, and you don't have to go far back in history to this old photo from John Handley back in 2004 of the Strubens mine, which was the first mine in the Witwatersrand, discovered in 1884. And interestingly enough, it was discovered in quartzites of the Witwatersrand group. And it was the first economic gold producer. It only lasted a year, but it did generate the interest in the Witwatersrand domain that really led to the discovery of the gold in the conglomerates and the gold in the reefs. That served us well for going on for 150 years. So the quartzites have had an important part to play in that arena, but it's also just worth remembering that the name Witwatersrand actually comes from the appearance of the white lower Witwatersrand rocks after rain, which looks like flowing water. So the ridge of white water is actually derived from the appearance of these quartzites. So quartzites have been a fundamental part of the journey in the Witwatersrand right from the very beginning. In putting my talk together, I wanted to really reflect on some of the things that I think are really important in the genesis of the mineralization in the Witwatersrand. And before I get into the detail of that, I wanted to just talk a little bit about the basin context, because the structural setting of the basin and the stratigraphy are really important to understanding everything about the rock sequence and especially the quartzites. I want to talk about some of the classification problems related to quartzites because we've got this wonderful SAC term quartzites, but in actual fact, generally when people talk about sedimentary basins, they talk about arenites or lithic arenites or wackies and so forth. And that doesn't work in Witwatersrand. So I just want to tackle that head on and explain why that is. And then move on into a fairly systematic discussion of the mineralogy and textures of the quartzites, some detail in the geochemistry, and then reflect on two really important aspects that I know have been covered in many of the other talks in the series. But there are a couple of things I wanted to mention, particularly about the role of organics and the role of structure in the evolution of the quartzites post-deposition. And then I've got two conclusions that I'd like to draw for discussion at the end. So kicking off with the basin context, this is a schematic cross-section of the Witwatersrand late in the depositional sequence. The brown is the West Rand group, the yellow is the Central Rand group, and it has a structural margin being a foreland basin, which is throwing up the granitic and other basement rocks to the west, and then leading to deposition into the basin. And that basic basin architecture really leads to four important considerations with respect to fluids before we do anything specific about the Witwatersrand. First one is weathering. And of course, that can take place in the hinterland, but also in the basin itself near the surface. And that is atmosphere dependent. And as you know, there's quite a debate that still rages about what the nature of the atmosphere was back in the Archean. The second important aspect, and this is particularly true for fallen basins, is the meteoric fluids that infiltrate, they're in equilibrium with the atmosphere, and they infiltrate under the hydraulic head at the edge of the basin. They tend to be very dilute. They're derived from rainwater, and they can flow long distances into the basin. The third part of the basin evolution relates to diagenesis and oil generation. And these are processes that happen in every sedimentary basin where they have organic material. And ultimately, diagenesis gives way to metamorphism and the high temperature assemblages that we see. Those processes tend to be sort of within basin in terms of their controls. And the fourth one that I've highlighted on this slide is the hydrothermal alteration, which by definition would be externally derived, introduced to the basin, and would be superimposed and interact potentially with all those other basinal fluid events. Diagenesis has been very well studied around the world, and it has some really important characteristics related to sedimentology and also some important implications that flow through in the early understanding of a basin as it evolves. And just to touch on some of these, firstly, grain size and sorting is obviously very important from the permeability and fluid throughput point of view. The proportion of matrix and clay is very important because it provides early sealing in shales, and it also provides reactive material for chemical alteration post-deposition. The framework stability is important because it controls both the mechanical aspects of rock deformation and compaction, but also the chemical response and the chemical variability for alteration again. And the depositional architecture is absolutely critical in terms of the flow pathways and which parts of the basin receive the maximum flow at any particular point in time. And there are two particular things that I'd like to highlight that are consistent with basin studies, but also the observations that have come out of the Witwatersrand. The first one is that the quartz arenites and quartz pebble conglomerates are silicified very early. And this is consistent with studies in other sedimentary basins where thin arenites, permeable conglomerates are cemented very quickly by silica moving in basin fluids. And the other thing that falls out of this type of analysis is the fact that it's impossible to look only at shales, only at sandstones or conglomerates and get a good understanding of the processes that are taking place. And that's really because there's an continuum between those different rock types, and what happens in one affects what happens in others. So that's the approach that I'll be taking through my presentation. And then finally, in terms of setting the scene, the lithological framework is really important. And there's just a couple of things that I wanted to highlight here. Firstly, there's two major groups. a Witwatersrand group, which is the thermal subsidence part of the Fallen Basin, which is dominated by shales and quartzites, largely marine sediments, and a Central Rand group series, which is much more quartzites and conglomerates. And most of the ore bodies, as you all know, are located in that upper Central Rand group. And so, in fact, all of the ore bodies are pretty much encased within quartzites. And so they must tell us something important, I think, about the processes that took place in those conglomerates. But also you can see in this diagram that you really end up with a series of permeable sandstones and conglomerates separated by shales and volcanic beds that effectively make this into a layered sort of permeable, impermeable type of sequence. And ever since I started work on the Witwatersrand, I've been fascinated by the fact that it's got three really strange features that are not common around the world. That said, they are observed in other Archean basins and some younger Proterozoic sediments as well. And just as a couple of examples, I've thrown in there the Dominion and Fortescue, which also have some of these characteristics. But they are quite mind-boggling in a sense, in that if you look at the Central Rand group where the mineralization is, there's virtually no feldspar. I personally have never seen a grain of feldspar in that sequence. There may well be a couple, but they're very, very unusual. The second thing is that there's a virtual absence of magnetite, ilmenite, and hematites in the mineralized stratigraphy. And to complement that observation, there's also ubiquitous pyrite throughout the mineralized stratigraphy. You'd be hard-pressed to pick up a piece of fresh Witwatersrand rock that doesn't have pyrite in it. So these are things that are atypical of sedimentary basins and absolutely critical to understanding the evolution of the Witwatersrand gold. And so in GenCore, we undertook a piece of work to look at the systematic alteration around the basin, because we knew from work that Neil Phillips and others had done that locally within shales and even regionally within shales, there was significant alteration. So we designed a program to collect samples based on collecting rock types and alteration systematically across the basin. And the sample sites that you can see here, the red dots and the mines, are where that work was undertaken. And I haven't updated the gold numbers here yet, but you can see around the arc of the gold fields towards the north and west, there's nearly 50,000 tons of gold that has been produced, whereas in the center of the basin, there's virtually no gold, a little bit produced at Witwatersrand. And our sample strategy covers the stratigraphy in the Central Rand group and parts of the West Rand group throughout that area. So we weren't collecting to collect gold, we were sampling to understand the systematic alteration around the basin. And that led us to the sample population that I'm going to talk about today. And this is what it looks like, basically classified firstly by lithology, where it's dominated by about 600 quartzites, but we've also got conglomerates in there, remembering, of course, the continuum between quartzites and conglomerates and the overlapping geochemistry between the two. And shear zones in the Witwatersrand are remarkably common. They cut both the conglomerates and the quartzites, amongst other things. And we've also sampled those because they have the same alteration assemblages in them. And we've made sure that we've got coverage across the West Rand group, within mineralization and outside of mineralization, and across the whole Central Rand group. And that population there also includes some shales. So there's nearly 1,000 samples that you'll see in various diagrams. And in reviewing the literature recently again, I'm quite surprised how consistent the information that is in our data set is with the information, the factual information reported in the literature. So moving on to why these things are a little bit of a problem and always have been in terms of classifying the quartzites in the Witwatersrand. And it goes back to some seminal work by Arthur Fuller back in 1958, who really undertook the first systematic study of Witwatersrand quartzites. And his conclusion was that there are lots of quartz arenites in the West Rand group. He used the term sub-greywackies to describe the lithic and arcosic sandstones with some clays in the West Rand group, but he noted that sandstones from the upper division, or the Central Rand group as we know it today, are interpreted as hydrothermally altered feldspathic quartzites. And this led to nearly 70 years of debate since 1958 as to whether this relates to alteration, some sort of depositional process, or potentially weathering. But, back in 1958, those 2.5 kilometers of Central Rand group, we already knew were very unusual in terms of their composition. So if you think about how people go about classifying quartzites generally in sedimentary basins, they use a diagram something like this, which looks at the amount of fragments within the rock, quartz, feldspar, and rock fragments, and the amount of matrix or clay material, which is the depth in the diagram, moving towards the field of quartz wackies. And so most sedimentary basins have those fields nicely represented. As I've said, in the Witwatersrand, there is no feldspar and there are very few stable rock fragments either in the entire Central Rand group. And that's because what's happening is that those fragments are being altered, forming clay minerals, and effectively moving you up in this diagram where what used to be feldspar and rock fragments becomes clay. And so quartz remains as the only stable component. And then you effectively move backwards in the diagram as your feldspar and rock fragments turns into clay material itself. So the net result is that you move upwards in the diagram and backwards in space in the diagram so that everything starts to look like a quartz wacky, if it's not a quartz arenite. And the process involves virtually every lay-bar grain or feldspar grain being altered. This process happens in situ. It preserves the sedimentary structures which are well described from the Witwatersrand. And effectively, the only rocks that are more or less like they were when they started are the quartz aranites. Everything else that we call quartzites are altered aranites or altered wackies of some sort. And it's often quite difficult to work out what. It has been suggested that the clay component is part of the depositional process. And I think that's largely being debunked now for a couple of reasons. The first one being that the transport of clay takes place in very different hydrodynamic positions to sand and conglomerates and pebbles and gravel, which are to the right of the x-axis on this diagram. So clay particles are transported in suspension at low flow velocities on the y-axis, whereas sands and gravels and pebbles are transported and then eroded and deposited in a much smaller space with very little actual area where particles are actually being deposited. So the way to get clay and quartz together, or quartz grains together, is really through debris flows. And this is work that's been done around the world in oceanic settings, where effectively debris flows lead to supercharged fluids where the quartz grains are in effect floating in a high density slurry of clays. And you end up with rocks that look like this one from the Welcome Goldfield. This is the middling quartzite, which is a genuine quartz wacky. You can see the irregular quartz grains floating within this clay matrix. No structure whatsoever, except where there's reworking. And there are these interesting zones where the clay has actually been winnowed out by subsequent winnowing, and you can see here the cross-bedded sandstones, which are now true quartz aranites, being dissolved from these wackies. If you then try and put that onto a standard classification diagram in terms of chemistry, there are a couple of interesting things that stand out. Firstly, and in these diagrams that I'll be showing now, you can see the rock types are coded by shape. Central Rand's in red, the West Rand's in green, and the size of the symbol reflects the gold concentration. And bearing in mind that these don't include conglomerates. So I'll point out to start that virtually every sample is anomalous in terms of gold, right around the base. And they may be very low levels, but they're above the background of about 3 parts per billion. Most of them plot into this litharonite, sublitharonite, arkose, subarkose field, which mineralogically makes no sense, as I'll show you in the thin section slides in a moment. So the only things that are really plotting in more or less the right part of the diagram are the shales and wackies, the squares, the triangles. These stars, which reflect the shear zones that I mentioned before, which are leaching silica and removing iron and effectively moving this population towards the bottom left of the diagram, and the quartz-aranites that have been sitting there doing not much. So moving into the mineralogy and textures of the quartzite population, here's a range of what they look like, and there are a couple of things I just wanted to highlight. So the first one is, this is the middling quartzite again, the wackies. You can see this poor sorting, the clay matrix, so a sort of a debris flow type deposit. These are two samples from the El Dorado Formation at the top of the Velcom Goldfield. You can see all of these lithic fragments of various types and different colors reflecting a different mineralogy. Some very dense in terms of their lithic content, some much less so with more quartz in them. But the important thing to note here is that the mineralogy of these is both the same, and it's the same as the other parts of the stratigraphy, although the proportions vary. Lower down in the Velcom Goldfield, you get the same sort of things. This is an unconformity surface with a coarser grained, quite felsic looking rock on the right, and then unconformably overlying that a much finer grained equivalent. You can see the color's the same and the mineralogy is the same across both of those. This slide over here shows a series of true quartz-aranite with a little channel with a conglomerate sitting in it. You can see the linear bedding here in the sandstone. So these are some of the quartz-aranites that have been relatively unaltered, but you can also see their transition into shale bands, which I'll address a little bit later in my talk. Interesting thing about these quartzites is that the local geos can pick them. So if you bring up a rock sample from underground, they'll tell you which formation it comes from, because in spite of the similarity in mineralogy, they have these textural features that are quite distinctive for the different goldfields and different stratigraphy. So if you take a population, this is a population we did detailed X-ray diffraction on, quantitative XRD, and you just look at the proportions of the minerals. The first graph there shows pyrophyllite and chlorites. All of the rocks have both of these in this particular case. I wanted to highlight these fields on the right here, where the chlorite is higher. Those are the El Dorado Formation, those black-looking rocks that I showed you, the dark rocks, and the middling quartzite wackies, which have a very high proportion of chlorite. Otherwise, it's generally pretty low. If you look at chlorite and muscovite mix, there's not a huge amount of muscovite. Chlorite does still dominate in that population. And then looking at muscovite and pyrophyllite together, that's also very common. But again, here at the bottom part of this diagram, you can see the wackies and those dark-colored El Dorado sediments having a fundamentally different concentration, dominated by chlorite with very little pyrophyllite and muscovite. The size of these symbols here again represents the gold content. So virtually every sample has low levels of gold above the background. If you plot those three minerals, you can get a better sense of their relative quantitative proportions. There's a lot of variation generally between pyrophyllite and chlorite, sometimes towards muscovite. I've plotted here on top of the diagram which samples contain chloritoid. So that's not XRD, that's mineralogical observation under the microscope. And you can see virtually all the samples, but not all of them, contain chloritoid, and that's because of a compositional control on the formation of chloritoid, which I'll talk a little bit about later. And again, you can see this population of unaltered wackies and highly lithic, dark-colored chloritic El Dorado Formation samples that are quite distinct from the rest of the Velcom Goldfield. If you look at those in thin section, and my sort of overwhelming sort of feeling was when I started my honours thesis and my master's thesis was just thinking how boring they are, because they all have the same minerals, and I had these piles of thin sections that all looked remarkably the same, which turns out in retrospect is a good thing, because it's telling you something about the scale and scope of the alteration that's taking place. But here you can see chloritoid sitting in a matrix, looks like an original grain, the matrix of chlorite and muscovite, muscovite around that, and there's very intense corrosion of quartz grains as quartz is consumed in these reactions. Here you can see pyrophyllite porphyroblasts forming in pressure shadows around pyrite grains. This is a chlorite porphyroblast being altered to muscovite around its edges. This is a muscovite porphyroblast, and again, you can see this intense corrosion of quartz grains in all of these fields. This is chlorite muscovite and quartz. And in this sample over here, you can see that what seems to have been original grains of something have been altered to this fine grained sericite mass, and in this case, a muscovite porphyroblast coming through it. So the overwhelming sense that you get looking at these things is quartz has been consumed, and a lot of these framework grains have been replaced by these sort of monotonous minerals, pyrophyllite, muscovite, chloritoid, virtually exclusively. If you take a chemical look at that same suite of rocks, looking here at aluminium, sodium, potassium, and calcium, and iron and magnesium, then you can see that they are very aluminous in terms of their composition. This is illite and muscovite, trending down in terms of their iron content. Again, those two parts of the population that I showed you before, towards the chloride-rich or iron part of the sediments. And again, the gold distribution, although it's at relatively low levels, that's 35 ppb for that second largest symbol, they're still well above background levels for gold in sandstones, or background gold in general. And still looking at that population from Velcom, a different diagram looking at sodium, potassium, and magnesium. And here you can see that actually most of the variation is in potassium, not in sodium and calcium, although I haven't included calcium on this diagram. So you're really looking at a mix that's controlled largely by magnesium and potassium, and I'll show you shortly that sodium has actually been removed from the system. And here you can see what I was talking about in those two rock types, the dark green chloritic wackies and the dark green Eldorado Formation with this very chloritic matrix, unconformably over the line, the more typical lighter colored muscovite-rich rocks of the rest of the Central Rand group. And so this is a piece of work by Andy Barnicoat and co-workers published in 1997, and they were looking to do the same thing, look at the regional systematics of alteration around the basin. And I think there's a couple of remarkable things about the sequence. So firstly, it runs from north to south, starting in Johannesburg in the north. It looks at the full Central Rand group stratigraphy and top of the West Rand group. And it shows the distribution of these mineral assemblages. And I've chosen these rather dull colors here because they do more or less correlate with what the rocks look like in the field in terms of the colors that represent these different mineral assemblages. A couple of things you can see about this is, number one, the alteration is channeled between the lavas at the top, the shales of the West Rand group at the bottom, and the Boycian shale. So you get these sort of tons of alteration moving right out into the center of the basin. And these red lines are the unconformities that host some of the conglomerates. And again, you'll see the alteration envelops and cross-cuts those unconformity surfaces. So it's definitely a feature that's post-depositional in terms of its superposition on the basin. In terms of the colors, these browns through the lighter green are all the slides that I've showed you in the previous examples. This top of the West Rand group, and for large parts of the West Rand group, has a very different assemblage that I'll focus on shortly. There are places in the West Rand group where you can get this whole assemblage visible in a single place. And so here's a photograph from Klerksdorp that shows a series of West Rand group quartzites transitioning from these relatively unaltered quartz, feldspar chlorite-rich rocks through into muscovite and pyrophyllite-rich rocks associated with conglomerates and carbon, and then transitioning back out on the other side. So you do find these alteration zones in the West Rand group, but they're a lot smaller. This is a long section that Neil and I put together to look at what the alteration looks like if you just travel around the northern and western edge of the basin. And this is a conceptual diagram. You'd obviously need a lot more detail than we have to fill it in with confidence in the detail, but I think the broad story is right. And there are a couple of things I wanted to point out here. Firstly, if you're a mine geologist working in a large gold mine, you never move out of one or maybe two of these alteration facies. So it's not surprising that people consider this to be the normal background rather than something unusual in the rocks themselves. And a lot of the more pyrophyllite and high sericite alteration is actually spatially associated with some of these carbon-rich parts of the conglomerate ore bodies. So if you take a thin section from that previous slide and you look at the unaltered Witwatersrand group rocks, they look something like this, where they have magnetite, ilmenite, sometimes hematite, and a range of stuff that you would expect clastic rocks to have. So basically all sorts of things that are rolled in, including a range of feldspars. They have carbonate cements, part of diagenesis. They have chlorite cements. They have secondary quartz overgrowths in places. Sort of rock you'd find anywhere in the world. Whereas if you go into the central rand group, you can see the clastic quartz grains, but everything else is gone. It's been replaced by muscovite, paragonite, pyrophyllite, or chlorite, chloritoy, and sometimes pseudoite. And commonly there are hydrocarbons associated with these alteration zones as well. And always pyrites. But as I said, you can't find a rock without pyrite virtually in the central rand group. So what are the processes that lead to that, and what are the implications of those processes? Which leads me on to the geochemistry. If you look at geochemical sections through the central rand group, in this case, this is from Clarkstock Goldfield data from Sutton, you can see that they are pretty unusual rocks in the central rand group, which is the yellow. They are very low in sodium, except for a couple of erratic places. They're very low in calcium, with the same exceptions. And they have very varied potassium, which is reflecting the muscovite concentration of these rocks. Sutton called this a stratigraphic control. And of course, it is stratigraphic in the sense that there are these variations that vary up the column, but also note that within every formation, there are very substantial variations that are almost as large as the variation in the entire column in the central rand group. And you can also see the very different chemistry of the quartzites in the Witwatersrand group, where you've suddenly got lots of sodium, lots of potassium, calcium, and much less potassium, which seems to have been added in the central rand group. So that gives you a sense of how fundamental these processes are in the central rand group. And if you look at that variability on a diagram, and this is the AFK projection, and I've taken Neil's work from some of the shales in the central rand group, and I've compared them to the quartzites for the entire GenCore population. And you can see that for the shales, they start off pretty much chlorite dominated with very little potassium. And then over time, they move towards muscovite and pyrophyllite, which are the alteration minerals that I've showed you previously. The key thing is that you don't really get out of the field of chlorite, muscovite, and pyrophyllite, and of course, plus quartz. When you look at the quartzites, the exciting thing about them is that they've got a completely different compositional suite over here, because this is the feldspar lithic fragment population that are showing up here. So in terms of alteration, you've got a suite of rocks that are much more able to record systematic changes. And what you can see on this diagram is the central rand group compositional variability, sometimes moving into this lower part, and then the Witwatersrand group much lower down in the diagram, sometimes moving into the upper part. And those are those alteration zones that I showed you in one of the previous slides. So ironically, the variability in quartzites means they're a great way to study fluid if the fluid is homogenizing the rocks. And that's what we can do with the quartzites. And so when the alteration processes take place, they take place through some pretty simple reactions, and you can observe these reactions in thin section. The first reaction there shows the reaction of feldspar to muscovite to release quartz. And these are hydrogen or acid-driven reactions. so that as acid is added to feldspar, you generate quartz and you release potassium into solution. This is the quartz that provides early cements in quartz arenites and quartz pebble conglomerates. That muscovite then goes on with the further addition of acid and quartz now being dissolved, reflecting back on those textures of quartz dissolution to give you pyrophyllite and again releasing potassium, which can move around and give you muscovite again somewhere else in the sequence. And this reaction shows carbonate cements being dissolved again with an acidic fluid to release calcium into solution. So the reactions for these alkali mineral rock types can actually be simplified and described in terms of how far these reactions have gone, just using the simple ratio of aluminium to aluminium plus these cations. So that in effect, as these cations are leached out, this alteration progress number approaches 1. And these reactions explain the early quartz cements, the consumption of quartz during the pyrophyllite reaction, the increased porosity due to calcite dissolution, the mobility of these elements, and these parameters control all of these reactions. And so they can be plotted up on these activity diagrams. And so this is the activity diagram that deals with the assemblage that has a lot of potassium and sodium. You can see the feldspar, muscovite, pyrophyllite, paragonite, albite, all of which are distrital assemblages in the Witwatersrand. And note that they all depend on this ratio, this activity ratio of the cation to hydrogen. And so there's 2 ways you can move on this axis. One, you can change the concentration of sodium, and the other one is you can change the concentration of acid or hydrogen. And so the general reaction in the Witwatersrand is towards muscovite, paragonite, and pyrophyllite and away from these other detrital components. And so in the original sediments, you would have had assemblages that covered all of these rock mixes in the quartzites. Whereas in the shales, you start off in these clay minerals right in the beginning. So your ability to record alteration is significantly reduced in shales, although it is very intense. You can do the same thing for the magnesium-potassium suite of clay minerals. Chloritoid sits in this part of the diagram. It's not actually shown in this diagram, but it would sit in the same way as paragonite does here above pyrophyllite for the appropriate concentrations. The key thing to note here is that because of the 2+ ion for magnesium, the activity coefficient here is squared, and so the effect of pH on these reactions is much higher. So to go back to the alteration progress, which is this reaction that I described earlier, you can effectively illustrate that on this diagram, which is aluminium to calcium and sodium and potassium. That line of 50 there is the feldspars. That's the muscovite paragonite line. And here you can see the green Witwatersrand group with a very large compositional range, as we showed before, and the red Central Rand group with a much smaller compositional range, although we do have these outliers. What do they actually look like in the rocks? Well, I've taken a range of thin sections here that show this alteration progress. So these effectively are just carried across here from the diagram. So alteration progress is reflected in your position vertically in the center of this diagram. So you can see that you can start off with a feldspar-dominated rock. As you increase the acid alteration, you move upwards in this diagram to the point where you've lost all your original grains in your sandstone except for quartz, and then you can end up with virtually no quartz whatsoever, with rutile concentrated along these dissolution bands, and effectively a muscovite pyrophyllite rich rock. So that's what that change looks like, represented in this diagram. You can do the same things with the ferromagnesian minerals, and I'm not going to talk to this in any great detail. I've put the reactions here, but chlorite can also consume quartz. These reactions lead to the mobility of magnesium and potassium, both of which can be mobilized in either direction, and we see evidence for these reactions moving in both directions. I've mentioned the sensitivity of these reactions to acid. And also wanted to note that with magnesium in particular, nickel and cobalt sit quite comfortably in the mineral structure of chloride. And so as chloride is destroyed in these reactions, nickel and cobalt are actually released into the fluid. And interestingly enough, they're a core part of the ore assemblage in many of the ore bodies. And that's really because of these reactions shown here, where muscovite can host lots of rubidium, but also strontium and barium, and chloride can host nickel and cobalt. So when you move this reaction in one or the other direction, you release these trace elements, which you can also track through the alteration sequence. And the same thing happens with carbonate, with strontium and barium, but not rubidium, being released by those reactions. In addition to those pH controls, there's also an important oxidation reduction control. Here is represented by the molality of oxygen. The effect here is on the sulfide minerals, pyrite, pyrrhotite, changing to oxides, but also on the stability of pyrophyllite, chloritoid, and iron chlorite. And as Hobbs et al. Have pointed out, pyrobitumen will bring you down into this part of the diagram, those hydrocarbons into the solution. But also importantly, because of this ratio of hydrogen and potassium, the fluid can easily be buffered to different pHs because of the mineral assemblages that are still stable. So in the West Rand group sandstones, for example, you would be buffered in this space, whereas in the Central Rand group, you're buffered in this space, with quite a significant loss of gold solubility across that transition. This is higher gold solubility, this is lower gold solubility shown there. So these reactions are driven by a dilute or highly acidic fluid. Sulfidation is not a major topic for my talk today, but I do want to point out there's abundant evidence for all sorts of sulfidation right across the sequence. They reflected in a simple way through these reactions over here to both pyrite and pyrrhotite from magnetite. But euhedral pyrite is very common, and it's very closely associated with the silicate minerals. Randor back in 58 and Myers in 93 have both described the sulfidation of ilmenite or rutile-rich iron grains, and Neil and others have described in great detail the sulfidation of pyrite in situ around the periphery of grains and so forth. So this is an important process in the bits as well. In terms of the mineralization, one of the things that's been very high profile is the supposed link between trital minerals, particularly zircon and chrome, and the gold concentration. So this is a classic diagram that Frimmel put together that supposedly shows this relationship. If you pick it apart a bit, though, it's not quite as clear. So to start with, this is three different reefs. And if you look at each reef independently, that correlation falls down pretty quickly. But perhaps more damning, the zircon concentration is not far off the crustal average for zircon, so it's hardly a spectacular range of concentrations. Whereas gold in the same diagram has a 6 order of magnitude variability across the left-hand side. So we decided to use our data set to explore whether or not we could say something about that mineralization and its link to heavy minerals. So the first thing we did was test the ratios of titanium, zirconium, and chrome and zirconium, representing ilmenite, chromite, and zircon, to see whether or not they actually correlated at all. And in this data set, I've included also the conglomerate samples that we collected, which are the open circles. And I think you can see pretty clearly that there's a pretty strong correlation between these detrital elements, would give you some confidence that they are in fact detrital. It's interesting to note that the conglomerates don't have a lot more than any of the other quartzites. They're all in the same ballpark. And none of them show dramatic concentrations above background, which are the blue lines in these diagrams. So doing the same thing that was shown in that previous diagram, I've looked here at chrome versus gold. The averages for the Central Rand Group and West Rand Group are shown in the usual colors. And you can see that, yes, there is a slight enrichment in chrome, but that enrichment occurs in virtually every quartzite, all the shear zones and the conglomerates. And the conglomerates, which host most of the gold, actually have no more chrome than the average quartzite does. So I think this is pretty compelling evidence to say that the inferred high concentrations of these detrital minerals is just not there. And you can do exactly the same thing for zircon. And in fact, the zircon concentrations for the Central Rand Group and West Rand Group are actually less than the average crust. And again, you can see this relatively small shift in the zircon concentration versus 5 or 6 orders of magnitude in gold. Very briefly, looking at some evidence for sulfidation and how that reflects in the geochemistry. This is the molar concentrations of iron and sulfur. You can see the pyrite line there and the data sets that I've described already. The size of the symbols again reflects the gold concentration. And you can see that the Central Rand Group have a wide spread, but they start to trend towards this pyrite line, whereas the West Rand Group have a much broader trend, but also trend into this domain. And the way that I interpret this diagram is basically that this part of the population are detrital mixes of silicates, iron oxides, and pyrite to give you the iron. And this part of the diagram reflects sulfidation of a variety of different iron minerals to bring you into rocks that are almost exclusively pyrites, but together with chlorite and some other iron-bearing minerals. And those are the ones that have the best gold mineralization. Looking at minerals that might be associated with the gold themselves, I've chosen arsenic, cobalt, and sulfur, and looked at them through their whole range of those different rock types. And there's this remarkable correlation that applies across all of those rock types, where cobalt and sulfur are enriched in every one of them. Cobalt correlates well with arsenic, and cobalt correlates well with nickel. So the elements that are moving around with sulfur are also the ones that form these unusual cobalt and nickel minerals in the ore bodies. Keith Kenyon put together this summary, which is a principal components analysis, and he identified an alteration suite, an ore suite, and a heavy mineral suite. And he asked the question, are they linked? I think our data can start to suggest that they are linked, and I'll show you why. So if you look at the alteration progress variable, that one that runs from 0 to 1, this is the line for muscovite, feldspar, and calcite, and you plot the detrital minerals, you'll see that between mineralized and unmineralized West Rand and Central Rand, there's basically no difference in those rocks, which would suggest that alterations have nothing to do with those detrital minerals. Whereas if you look at gold and uranium, then you can see something dramatically different. As soon as you cross that muscovite line, there's an explosion of high values of gold and of uranium in all rock types, not just in the conglomerates, which are the open circles, to numbers that are well above background, not necessarily mineralization levels. And if you then look at alteration progress versus the base metals, you can see that copper and zinc have also got nothing to do with this alteration that we've been describing. And that's consistent with base metals not being an important part of the Wits assemblage. And here's cobalt and arsenic, and particularly arsenic, you can see again that in these highly altered rocks, arsenic is widely distributed, including in the ore bodies, but also in other lithologies, particularly quartzites. So quickly onto the role of organics in this whole system, and I'll really just point to two facts here. The first one is that there is widespread alteration in the shales. It's associated with other types of alteration in quartz arenites, for example. But the key thing here is that these shales contain about 0.2% organic carbon today, which means that they could have hosted up to 3% in the original sediments. When you put a hot fluid through that, you'll take hydrocarbons into solution, and you can, at 300 degrees, for example, you can dissolve 5,000 ppm of hydrocarbons in solution, which is quite remarkable. These things are metastable at 300 degrees, but they can sit quite comfortably in solution. And that makes them available to do two really important things: affect the redox and affect the pH, and potentially drive that acid reaction that I've described previously. Couple of thoughts on the role of structure. Wall and Hall put up this diagram in one of their presentations recently, and it just shows that for this section, which is 60 meters thick, with a range of mineralized conglomerates, with lots of gold through the sequence in a range of different lithologies, there's widespread pyrite, stylization, foliation, pyrophyllite, pale mica, and green mica, which is probably fuchsite. So the types of textures that I've been showing you are by no means unusual when people go out there and look for them. And this is what some of those structural features look like. These are clay-rich zones sitting underneath the Peritus Reef in exploration boreholes. These are 5 intersections of the same reef. You can see this very intense clay alteration underneath, and fractures filled with chlorite sitting in the overlying quartzite. Quartz veins linked to chloritization. This is the basal reef overlain by the clean bar, completely dissected by these cross-cutting fractures and filled with vein quartz and sulfides. And these are Velcom Goldfields quartzites being completely transitioned into clay minerals. You can map those structures underground. This is what they look like, where you can see that what are originally siliceous quartzites get almost completely replaced by clays to give you these argillaceous-looking conglomerates, and thrust faults move these shear zones around, and they themselves are altered as well. Richard Spencer and I mapped hundreds of meters of drives in Evander to illustrate these types of relationships. If you look at a quartzite that hasn't seen this alteration from that previous diagram, and you map it into a shear zone, then you can see this transition, where you eventually end up with no quartz virtually, lots of silicates, and rutile, which is left by the volume loss related to the alteration. If you plot that on an isocon, you actually find that there's been a 60% volume loss. And you can see here in this diagram just a trivial little shear zone running across the bottom of this band of chert pebble is almost taken out the whole chert pebble through dissolution. This process is really important. It occurs in hundreds of meters of Witwatersrand stratigraphy and must have caused a significant thinning of the stratigraphy through the process. So in conclusion, two conclusions. The alteration in the WITS seems to be spatially and chemically linked to mineralization through two processes. Firstly, acid alteration associated with hydrocarbons, which takes out all the feldspars, leaves you with these quartz-depleted, clay-rich rocks. And secondly, at the same time, sulfidation reactions that both replace magnetite and hematite, but also precipitate secondary sulfides to give you rocks that have no iron oxides but abundant euhedral pyrite. So this reflects the addition of excess sulfur, and this reflects the addition of excess hydrogen ions to drive those reactions. And the second conclusion is that the mineralogy and geochemistry of quartzites are consistent with very widespread alteration and hydrothermal controls in the mineralization. And so what I've done just in summary in this table is just to look at a range of predictions that are made with respect to the placer model and the hydrothermal model, starting with alteration control, which I hope I've shown is pretty consistent related to the quartzites and the enclosed ore bodies. The placer model doesn't predict any. In terms of element associations, this is a myth that they associated with these heavy minerals. There's no base metals that you would expect if there were triple sulfides, but there is this very strong association with arsenic, nickel, and cobalt, which at least in part can just be derived locally from the interbedded shales through this acid alteration process. The placer model It doesn't require any sulfidation, but the hydrothermal model suggests it'll be widespread and linked to gold and alteration. And I think, again, there's pretty compelling evidence that it is. And finally, sedimentary facies. Some of these alteration trends that I've shown you cut across a whole range of rock types. They've got nothing to do with sedimentary facies, and the mineralization also cross-cuts those facies, which again, I think suggests that hydrothermal alteration is a very important component of the mineralization. So thank you. Apologies for going slightly over time, but I'm very happy to take questions.
Jonathan, thank you very much. That was wonderful. We will take questions, but just before we do, I want to make a comment, and I stand to be corrected by people who have listened and worked on the bits a lot. I don't think I've ever heard a public talk, a full public lecture on the quartzites of the Witwatersrand that are right across the basin. So I don't think I've ever heard it all put together like that before, which surprised me a little bit as I was listening. So well done for that. If others want to correct me, they can. I'll take questions from anybody there.
Neil, can you hear me?
Go ahead, John.
Okay, I'm not a gold geologist. I know a bit about the bits, so fantastic. Yeah, great talk. My question then is, where does the gold come from?
Great question. I don't think it comes from within the basin. So I think it's coming along these marginal structures from a terrain that must have a very high geothermal gradient, and probably comes from the same place as greenstone hosted gold comes from, which is, I think, dehydration of some sort, either of underlying volcanic sequences or potentially dehydration of a subducted oceanic slab, and the fluids being carried up into the upper crust from there.
Okay. Yeah, and then again, a question as a non-Wits gold guy, but you've got all those zircons, and one of the things that strikes me is if I look at all the work done on the mantle and kimberlites and sources of diamonds and diamonds themselves, isotopes have figured quite prominently. Surely, if you have all this thermal activity and fluid moving around, isn't there a way of getting stuck in and looking at some of those zircon populations to help, perhaps unravel the model, or is that not the case?
Yeah, it's a good point, John. I think it is useful, and in fact, Keith Kenyon and the Anglo team actually did quite a lot of work on those zircons. So it might be a question to direct at him. But I do know that although the zircons are remarkably unaffected by the alteration, there is a little bit of zircon precipitate that is hydrothermal zircons. And Keith and the guys have done some work on dating those zircons to try and infer the age of some of these alteration events. It's a bit difficult to link them in specifically, though, to a particular event. But overall, the zircons, are virtually unchanged. They just sit there. They one of two minerals that really doesn't seem to do much. The zircon and the chromite really just seems to sit there and not change.
Yeah. Okay, fascinating. But I think at the end of this series, Neil's got to put together a 5-point plan of all the couple of critical things that need to be done as a follow-up to all this fantastic work. But thanks, that was excellent.
That sounds like my homework. Thank you, John. To Jonathan, I am aware of what you said about the mine geologists are very good looking at something and saying that's the XYZ quartzite and that's the something else. But do you know exactly what they're looking at? Is it just textures of grains, or is it alteration or something else?
Yeah, it's a combination of everything, Neil. They do it with sort of a magical sort of I don't know, some sort of scanning process, but I think fundamentally it's the sedimentary texture, it's the color which links into the alteration, it's the discoloration of facets, which some formations tend to have and others don't. It's the textures, some are yellow speckled, some are green speckles. Things like the middling quartzite just have that massive appearance and the color that's associated with them. And each mine geologist gets to know their particular mine. I don't think there's anything universally consistent. It really is sort of an image processing thing that the human brain does that brings all these factors together and just makes them visually different.
Yeah, no, it's really interesting how they do it, and it looks sort of puzzling, but it would be nice to then convert it and say this is actually what is being recorded. But anyway, it's impressive the way they do it.
Yeah.
Jonathan, can you hear me? It's Trevor here.
Yes.
Trevor, go ahead.
Yes.
Just a comment on the nature of the alteration and comparing that to what we've seen at Barberton. The quartzites of the Moody's at Barberton are particularly high in feldspar, about 30% feldspar, and have a lot of oxides, and have never been found as a source of gold in that primary sense. But there are a couple of places like at Agnes Mine where you do find alteration creeping in through these layers. And what you see in those zones of alteration are the same as what you've seen in the Wits, where you have the removal of sodium, the removal of calcium, the concentration of potassium, and the same sort of mineralogy developing. So it's actually quite interesting to see the tie-up between the mineralization and that mineral change.
Yeah, well, that's fantastic to hear, Trevor. I wasn't aware of that, but it's exactly what we'd predict. And, one of the things that's always worried me about the Witwatersrand is that although it's unique in terms of its gold concentration, the style of the alteration isn't unique. And so whatever the process is, has to be quite a widespread process in the Archean. And to hear it articulated like that from Barberton is very encouraging. And I know that things like the Dominion Group, and I believe even some of the conglomerates in Barberton have similar alteration assemblies associated with them. They're just much smaller and less intense.
Yeah.
I don't think Spike McCarthy is on tonight, but today, but he's alluded in previous ones of these about similar alteration in other parts, and I'm talking about hundreds of kilometres away, where people have been prospecting for, I guess, Wits lookalikes or extensions. So I guess the answer is yes, that those things are widespread, as you said.
In a different presentation, I could give a talk that looks at a range of sedimentary basins and compares their geochemistry and alteration to the Wits. And the one that stands out as an obvious comparison is the Fortescue in Western Australia, where all the same sorts of things apply, but the scale of alteration again is a lot smaller, less intense, and also hasn't been terribly well studied.
John, go ahead. Sorry. Okay, look, we might wind it up there. Let me remind you that next week we've got Matt Mullins, and it's another talk looking at a lot of data, a person who's looked at a lot of the Wits underground. And then the week after is John Parnell, again looking at the data, but focused very much on the carbon and saying, what are the observations? So we've got two interesting talks coming up following Jonathan Law today. Jonathan, thank you very much. That was fabulous, and I hope that it gets used a lot in graduate classes and so forth. There's a single lecture, quartzites, and that's the story. So well done. Thank you.
Thanks, Neil, and thanks everybody for coming.